Our first speaker of this next section is Dr. Mike Lawrence of Natural Building Systems. Mike is a director of research there, and he is going to talk to us about hemp-based products.
Just a little overview of bio-based construction materials. Why do we use them? Well, they do confer a lot of benefits: breathability, specific heat capacity, hydrophobicity, and carbon capture. So these are benefits that a building actually uses and are very interesting. But there are some problems with it. One of the issues is biodegradation, is that a bio-based material is by its nature biodegradable. Fire resistance, a bio-based material is carbon-based. Carbon and oxygen combine with heat and they burn. Certifications. In order to build a building, generally speaking, people will want to have funding for that building, and they're not going to get funding unless they can get a warranty, and they're not going to get a warranty unless you can demonstrate that it is fit for purpose. And in order to be fit for purpose, you need to have a certification, and certifications cost a lot of money. Generally, most bio-based construction companies are fairly small SMEs, and they don't really have the funding to build to get a certification. So that is a problem. And availability. If you can't get hold of it, you can't build with it, and farmers aren't going to grow it unless you buy it from them, and you're not going to buy it from them unless you can have a market, and you're not going to have a market unless you can prove that what you're doing is fit for purpose. So those are some of the issues that we have to address, and we're going a long way towards addressing them. A typical house, standard timber frame house, has a very high carbon footprint when you build it. You can reduce the carbon footprint a little bit by building it off-site, building it in a factory, using timber as part of the structure, and you can get down to about 300 odd kilograms of carbon per square meter of floor area. What we're trying to do is turn the thing on its head, and we're trying to make buildings which actually take carbon out of the atmosphere. So we use entirely bio-based materials, and not only that, but we make sure that they meet the standards required so that we can get a warranty. And we are in the process of doing that with our construction system at the moment. And our construction system is designed to actually be part of the circular economy. So the system that we've designed consists of, if you like, giant Lego blocks, which you put together to have your building. And then when the building reaches its end of its useful life, you can disassemble it readily and then repurpose it to another building. And that is a key to what we have been trying to design. Doesn't really like me, your machine. It does, it's just. One of the interesting things about using particularly hemp is its ability to moderate the internal environment of a building. So it has a very interesting pore structure, and I've got some images of that in a minute. And what it tends to do is, if you get a very high humidity in a building, it will suck that into the walls. And if it goes very dry, it will push the humidity out. So you maintain a really nice steady level of about 50 to 60% relative humidity. And guess what? That is the sweet spot which stops growth of bacteria and viruses, which stops very dry atmospheres which are really not very good for the health. So that is a passive way of managing the internal environment without the need for air conditioning. Hemp is the material that we use, and we have a particular material that has been patented, which is this stuff, which is, you've probably heard of hemp lime. Well, this is hemp without the lime. I'm using a different patented binder. It actually performs better than hemp lime in a number of ways. But the key thing is the moisture buffering, where if you get moisture buffer levels of above about 2, wherever your figure is here, above 2 is what they call excellent. Well, we're at 2.91. We're well over the excellent. And what that means is that it manages the change in humidity really effectively. We've also got very low thermal conductivity values, so it's managing the internal thermal environment. We are particularly interested in hemp, and that's why one of the things we're in this CHCX3 project. We're looking at manufacturing not just hemp-based materials, but also working with other materials. But on hemp, what is so interesting are the relative different sizes of pores. And what this allows moisture to do is to move through the pores and condense and evaporate. And in doing so, you're making use of the energy involved in changing phase. And this gives it an increased thermal mass, much more than its physical mass. There are 2 parts to the hemp plant. So your old hemp plant here, after it's been retted, you can take off the fiber and you're left with the woody core inside, which is what we call the shiv, which is this material here. And that is the material which we use to manufacture our hemp sil. The hemp fiber is really useful for making fibrous insulation, very low thermal conductivity insulation. One of the problems you have to be aware of with hemp lime in particular is it uses a lot of water when you make it. And if you don't get rid of that water, it hangs around. And when it hangs around, you can start to get mold growth. One of the interesting things that I've been doing a recent experiment with the hemp sil, I stuck this into an environment chamber at 95% humidity at 23 degrees. And the standard test for biodegradation is, will it last 28 days without mold growth? If you have no mold growth, you get a 0. If you have the whole thing covered in mold, you get a 5. And interestingly enough, we've gone 5 weeks and I haven't spotted any mold growth. So we are very resilient as a material, which is a very encouraging thing. Another plant that we're quite interested in is miscanthus. Here is a board I've made recently using our binder, our patented binder, with miscanthus. Because of the length of the pieces of miscanthus, you get a better tensile strength. And what I'm hoping to do is to develop this material into an alternative for wood wool board, which is a really interesting material which has very good acoustic properties, and it's also very fire resistant. And so I'm working on developing that, and also on using it as a render carrier. It has a different pore structure, but nonetheless, it's got a very good insulative properties. So we're sticking these together with different binders. We're using a range of different binders in this project. So the hemp sil binder, a mylofoam binder, which is another mineral binder that I've developed, which is completely fireproof. and a geopolymer, which is like a cement, but a lot less carbon involved. And you can actually manage the way it dries and sets much more readily. And then thermosetting binders, we're working on a bio-based thermosetting binder. This is some material that we've developed, which uses a thermosetting binder, which contains no VOCs, no formaldehyde, no petrochemicals. And then we are going to also be looking at bio binders, mycelium, but that's a little way in the future. We are currently starting trials. We're waiting for materials to come from the farms because the CHC project has only just started. And as new materials come, we're going to be trialing them, making boards out of them at different densities. So either the very low densities here, or this sort of density, which is a bit less dense than MDF or OSB, but has similar structural properties. And we can even go the whole hog and make something which is very robust indeed with the thermosetting binder. And we're first of all trying the binder variations, and then we're going to start varying the aggregates, adding fibers, and all of this is to evaluate the different materials that this CHC project is going to produce, so that we know what is best for use in the construction market. So the idea is that we should make materials that are climate friendly, moisture regulating, and our particular system is the adaptability. So each of these little cassettes can be taken away and reconfigured, all without any unscrewing or anything. They're all just held together by clips, which are taken apart, and 100% of the building can be repurposed at end of life, which is what I think is so exciting about it. And that's it. Thank you very much.
Mike, got time for a quick question for Mike?
Yeah.
Yes, Kevin.
Is that a new build, or can that be done on retrofit?
It can be done new build, and we are also looking at retrofit. In fact, there is a project that's just been funded partly at the University of Bath, and we're hoping to work with them to develop. Well, we have a system conceptually which we want to use in retrofit, because that's the focus of their project, which is a 3-year project, and we will be delivering to them and they will be evaluating it. So retrofit is a difficult area to get into, because you lose space and buildings aren't exactly the right shape. But we've developed something which adapts to what's required there, and we think could be very exciting in retrofit. Yeah.
Any more questions for Mike?
Yeah.
Just Nigel.
I was curious as to the relative cost.
Our aim is to have cost parity. So, for example, I'm actually putting an extension onto my house at the moment using this system, and it's going to come in at around £1,400 a square metre, which is pretty much cost parity with the traditional methods.
Lydia?
A quick one. I hope it's not an unfair question. So there's degradability, and there's actually using that degraded. So I'm wondering how easy it will be and cost effective to use your components in a new build.
Sorry, in the context of degradability?
In the context of end of life, you're saying we can take some of those components and put them into a new build or whatever. Yeah. How?
Well, so why do you get degradation? You get degradation almost 100% because of water. So what you have to do in any building is to design so that water doesn't hang around. And if you design that building properly, you know, you get a rainstorm, you get a flood, whatever, water goes away. And provided that it doesn't degrade, certainly in terms of flood, if it doesn't degrade in the period when it is flooded, then you're good to go. If you design a building badly and you get water hanging around, that's when you get the problems. And you know, we talk about hemp lime. Everything that I've ever been asked to do at problem solving with hemp lime has been fundamentally because of water, because either it's been sealed within the system and not been allowed to get out, or it's been the design has been poor and water has come in and again not been able to get out. You have to design a building properly. If you keep it dry, it will go on forever. You know, look at even in this part of the world, you'll see timber frame buildings that are 1,000 years old and they're fine, because they've been designed properly and they don't allow water to hang around.
Great, thank you very much, Mike.